Hi everyone, I'm Ciaran from the Irish Centre for High-End Computing. This talk will be about integrating a tape-capable object store called Phobos as a Lustre HSM backend. First, I'll give a brief overview of who we are. I'm part of the Performance Engineering Group at the Irish Centre for High-End Computing, or iCheck. Established in NUI Galway in 2005, iCheck is Ireland's national HPC competence centre. We currently have offices in Galway and Dublin, and we manage the national HPC infrastructure, named K. This is a collaborative project with CEA and DDM, and a member of the CEA team will also be presenting an overview of Phobos, the object store, during this talk. iCheck's original function was to operate Ireland's first national academic HPC service for the benefit of all Irish higher education and research institutions. This service has continued, providing support and training for academic usage of our supercomputer throughout the country and providing HPC-related courses at a number of universities. Furthermore, we have expanded to additional areas of research around HPC independently, including novel technologies, environmental sciences and geophysics, as well as a large number of public sector and commercial engagements. We will begin with the motivation behind this project. Then we will give an overview of each of the components. I will hand over to Sébastien from CEA for the first one on Phobos. I will then return to provide an overview of the other two components, Dymos and Estuary, and we will finish with an overview of the full pipeline and a simple example of how it will be used. Exascale computers are just around the corner and will require huge amounts of data to ingest, petabytes per day, and exabytes to store. In order to overcome POSIX file systems bottlenecks, extremely scalable storage will be required at reasonable prices. As a cheap, energy-efficient, and durable medium of storage, tape libraries provide a feasible solution for long-term storage, or archiving. Object stores provide good horizontal scalability and are widely adopted for internet services, cloud computing, and much more. That brings us to the main motivation behind this project, which is to provide an extension to Lustre parallel storage onto a cost-effective central object store with a pipeline provided by open source tools. Phobos is an open source project maintained by CEA that provides tape object storage at scale. Overall, the aim is to integrate Phobos with Lustre's hierarchical storage manager using a common data access paradigm such as S3 or Swift. To enable Phobos to be used as a Lustre HSM backend, two intermediary components were required, a connector for Phobos and a HSM copy tool. For these, we decided on an S3 connector for Phobos in the form of an open source S3 web server for interfacing with object stores, as well as an S3 HSM copy tool. These will either be developed as open source projects or using pre-existing open source projects.
Hello, I am Sébastien Gougeaud from CEA and I will present you Phobos. Phobos stands for Parallel Heterogeneous Object Store and is an open source project developed by CEA since 2014. It was designed in order to manage an heterogeneous set of storage resources, first including magnetic tapes in SCSI libraries as an object store. It means that you can easily put and get objects from it and into it, select in which tier your objects will be stored, and this with optimized I/O for each technology. Since 2016, Phobos is used in production for transgenomic, thus handling multi-petabyte genomic datasets. To describe how Phobos works, we will take some time detailing its current main features. First, from the bottom right of the design, I/O adapters are used to access data on media, one adapter for each storage technology. This is where the optimizations on I/O are made. Two are currently available, as we handle both tapes and file systems, but others can be implemented, like object stores. Just above, we have data layouts, for performance and/or fault tolerance. For now, we only manage mirroring, but others like striping and erasure coding are envisaged. Media tags are used to partition the storage system. They can be used to target a specified storage tier, for instance by using an archive tag if we want our objects to be stored on magnetic tapes, or a fast tag for NVMe. Or we can also choose to divide the system in N parts with N the number of projects we deal with, to set up a quota feature, for example. The resource scheduler has the heavy task to prepare media in a smart way. Operations on tapes take a lot of time, and our goal is to minimize it, so we can increase the tape fill rate or reduce the number of tape mounts. Finally, object metadata, which also include layout parameters, are stored both in a PostgreSQL database used as an OSQL-compliant key-value store to ensure fast access to object information, and on media to allow tape imports or, more unfortunately, recover from failures. To feed Phobos with objects, we built a command line interpreter and an API, which can be used to connect to an NFS, Swift, or, as showed in this presentation, an S3 server. So, what is expected for Phobos in the coming years? First, some features we think are mandatory, as object deletion and versioning to support more S3 API. We also plan to improve the resource management with media lifecycle, garbage collection on data, and media migration. Our main goal is to get an exascale-ready version of Phobos, and for this purpose we need to offer a multi-server parallelism and work on media allocation optimization. And because we are really close to our production team, we take time to develop requests they ask us, to ease their work. Now, back to the main topic and the other moon of the Red Planet.
The next stage is to implement a web server that acts as an interface for storage backends. For this purpose, we chose the S3 protocol, since it is common and widely supported. Currently, Dymos, or Delivery Endpoint Interface for managing object storage, supports the operations put, get, head for metadata retrieval, and object listing. We also support the S3 authentication mechanism for request approval. As this project is open source, you can find it at the URL given here. In terms of design, we have taken a very modularized approach with 3 distinct parts that interface with one another. The project is written in C++, and we use virtual classes to implement abstractions for each of the 3 components. The server component handles requests. The stream component handles passing data received by the server to the storage component, which handles interfacing with the storage backend. We currently have 1 implementation for each of the components, inheriting from the base classes. The server component has an S3 implementation, as mentioned before, based on Facebook's highly parallelizable open source library, Proxygen. The stream component has an implementation using Phobos. This allows us to take a zero-copy approach to transferring data from the server to the storage backend. And the storage component, of course, has an implementation for interfacing with the Phobos API. Each component was also designed with parallelization in mind. So, Dymos will sit on the same machine as Phobos, handling requests for storage or retrieval of data in the object store. The intention, of course, is for this data to be archiving data from Lustre's HSM. We are still quite early in the development of Dymos, at least in relation to our supported S3 feature set. These are some of the features we are aiming to support in the future. For those of you who are not familiar with S3, objects are stored in what are called buckets, which are essentially a means of categorization or organization of objects. As mentioned earlier, we support the listing of objects in a given bucket, but not yet the listing of buckets themselves. 2 other somewhat related features we wish to support are object deletion and object versioning. We also plan to support multi-part uploads, which allows a large object to be broken up and sent to the server in parts, where it is reconstructed. A rather large future undertaking will be to create a distributed Dymos system for interfacing with distributed Phobos instances, each with their own set of tapes. The Dymos server will also be extended to support additional protocols, such as OpenStack Swift. The final missing part for achieving a full pipeline from Lustre HSM to Phobos' object store is an S3 HSM copy tool. Compute Canada had previously implemented a clean S3 copy tool, but ceased development on it about 5 years ago. It was relatively straightforward to update the project to comply with newer versions of Lustre and libs3. The copy tool gives Lustre's HSM a pathway to Dymos via S3 for archiving files or retrieving archived files. This project can again be found at the URL here. This is something like what the full pipeline looks like. From the Lustre storage units, data can be copied and retrieved over Estuary, Dymos, and Phobos to the tapes, structured by the SQL database. We will finish up on a simple example of how the full pipeline will operate in practice. Here we have two machines, one running a Lustre file system with the Estuary copy tool integrated, the other running the Dymos web server and Phobos object store daemons. A simple example of the operation of this configuration would be to, on the Lustre machine, archive a file, release the file, and restore the file to the Lustre file system. In turn, the file will be received by Dymos and passed to Phobos, saved to the object store, and eventually transferred back in a similar manner. These are the corresponding commands, illustrated diagrammatically. The HSM archive command archives the file. The HSM release command removes the file from the Lustre file system. And the HSM restore command retrieves the file from the object store. The orange square shows on which machine the contents exist throughout the process. Now I'll show you a quick demonstration of this procedure. I'm running a single virtual machine, so file transfer will be over localhost. So we have a Lustre file system mounted here, and it contains a single file. Before we start, we must set up Dymos and Estuary. Phobos daemon is already running, as you can see here. So we start the Dymos server listening to localhost. That should be running now. The Lustre HSM is already set up, so we just have to start the S3 copy tool. Just follows. That's on the Lustre file system. Okay, so that's running too now. So now we're ready to archive. The Lustre file system, just before we start, is 184 kilobytes, and that's before executing any of the HSM commands. So now we'll archive a file using the HSM archive command. Okay, so that is archived now. The local file is actually unchanged, and that is until we execute the HSM release command, and this is what deletes the file from the Lustre file system. So as you can see, the file contents have been archived, and they are currently not in the Lustre file system. So the file can be restored to the Lustre file system using the HSM restore command, but in fact any attempt to read the file will result in the file contents being transferred back. So we will just simply run cat file, and just to make sure the Lustre file system is now 184 kilobytes in size again. That's the end of our talk. Thanks for listening. If you have any questions, we will be happy to answer them now.